This is a continuation of the previous problem. Before we were looking at part A, we found that the mass of block 2 could not be more than 1.8 kilograms, or else it would be too heavy for friction to hold block 1 in place, and the whole thing would move. In this situation here, we're saying using the value of M2 found in part A, so using that 1.8 kilograms, find the acceleration if the block is nudged and put into motion. The interpretation here is that we know that kinetic friction is less than static friction, and so if we nudge the system a little bit, we are effectively reducing the amount of friction that's acting, because if we nudge it, we push it into the kinetic regime. And so now, with less force holding it back, it'll start moving. It was just on the cusp of moving before we did anything. Now it'll definitely start moving, and we want to find the acceleration of the system. So I've left everything up to show you the changes that we would need to make. A couple things here. If it remains motionless, that's no longer true. Now we're told that the block is put into motion. And so we can say that our acceleration here is not 0 anymore. And that's what we're going to try to find. The forces are still all the same as they were before. We said that we're put into motion now, so one thing that's changed is the acceleration and the velocity are not what they were. And so now we'll need to put into new velocity and acceleration vectors. So if M2 is very heavy and it starts sliding down, it's going to drag block 1 behind it. Both of them, I should say M2 is going to go down the incline, M1 is going to be pulled across the incline. And what we can see here is that because they're connected by a string, we can say that velocity of 1 in the x direction is going to equal velocity of 2 in the x direction as well. We're just going to call that some velocity. We can say that the acceleration of block 1 in the x direction is going to have the same magnitude as the acceleration of block 2 in the x direction, and that's just going to be some acceleration, because if the rope is inelastic, as one moves, the other one's going to move a corresponding amount. So we have these acceleration constraints that we're going to declare here. The rest of the free body diagrams are all correct. The only other change that we should make here is that we now have a kinetic friction rather than a static friction. But again, all the other forces are all exactly the same. Now we can come over to the Newton's second law equations. Before we had all of the accelerations were 0, now the acceleration is not 0. So we will now restore our equations to what they were. Again, we have not a static friction, but a kinetic friction now. We said that the two blocks are accelerating in their respective x directions the same, so I can erase the subscripts here, because these two accelerations are the same acceleration, right? The acceleration in the x direction for block 1 is the same as the acceleration in the x direction for block 2. They have the same magnitude, and so we'll represent them with the same variable a. Block 1 is moving across a horizontal surface, so it's not moving vertically, so its acceleration in the y direction is still 0. The same thing about block 2, it's also moving along an incline, so its acceleration is still 0 as well. So when we made this change about putting the block into motion, we had to change a few details, but our force identification, our free body diagrams, and our first set of equations were essentially the same. Now we'll need to erase all of the stuff that's left and redo the calculations from here. So here we know M2 was 1.8 kilograms. That was what we found in the first part. We also know the mass of block 1, so we know the weight of block 1. We know the coefficient of friction, so we should be able to simplify the kinetic friction as well. What we're looking for here is the acceleration. What happens a lot of times in these sorts of systems is that we don't know the acceleration. That's what we're trying to find, right? We're being asked what is the acceleration. We also don't know the tension, and so we typically have a situation where we have two equations, two unknowns, and we'll have to solve for the acceleration. What we'll do now is go look at each of these equations separately, and we'll try to plug in the values for each one of those. So kinetic friction is always just the coefficient of friction times the normal force. the normal force of block 1 here. The weight is always mg. We talked about how the x component of the weight for block 2, the x component is this side here. The full value of the weight is m2g is the full value of the weight, and then this x component here is opposite that sine 40, opposite that 40-degree angle, and so we'll have a sine 40 degrees to give us that component. And the same thing with the y component of the weight, we'll have a cosine of 40 degrees. So again, we can say here, from this equation, that the normal force on block 1 is the same as its weight if it's on a horizontal surface with no other vertical forces. That is pretty typical. We can take this value and plug that in up there. So effectively we had 3 equations, 3 unknowns, and we just eliminated the normal force as an extra variable. I'm also going to take this equation and write this down here as well. And now what I have is this expression equals that expression. Also this expression equals that expression. And so what I can do is I can add these two together, and I can add those two together, and they should still be equal. This plus this should equal this plus that, because these two are already equal and those two are already equal. So if we add those together, they should still be equal. Notice when I'm adding them, I'm going to have t here plus a negative t, and those are going to cancel. That's the whole point of pulling that trick. What you'll notice here is I have 2 forces here. These are my 2 external forces driving my system. I have the weight of block 2 pulling me down. I have the frictional force on block 1 holding me back. Those are the 2 external forces. All the other forces are internal to the system or are otherwise balanced out. I also have 2 terms here. I'm trying to solve for acceleration, and in fact, by putting all my acceleration terms here on the same side of the equation, I have a common factor that I can factor out. And then to get acceleration by itself, I can divide through by the mass. And so now all that's left is for me to plug in. And I find here that the acceleration is 0.842. That's an acceleration. It should be measured in meters per second squared. I have 2 sig figs everywhere, so I'm going to round this to 2 sig figs also and say my answer is 0.84 meters per second squared.